Before 1897, scientists kind of get an idea that many nuclei undergo spontaneous decay and emit some form of radiation, but they didn't know what the radioactivity was at the time. Okay, in 1897, Ernest Rutherford did his famous gold-foil experiment. He used the iridium nucleus, which undergoes radioactive decay, produce alpha particle, and that's how he record his experiment. Marie Curie, when she started her career, she didn't know what the radioactivity was, and later she discovered the radium and polonium. Pierre Curie, who is Marie Curie's husband, he is the pioneer of X-ray crystallography, magnetism, and radioactivity. And last one, we have Henry Becquerel. He's the one who discovered radioactivity. Okay, and some of these they share the Nobel Prize. Anyway, so throughout the years, there are 5 common types of radiation. Okay, the first one we call an alpha radiation. In this case, the alpha particle is released from a nucleus. Okay, so the alpha particle comes out. So in the experiment, there are a lot of experiments to identify alpha particle. All right, but one of them is to have alpha particle goes through the electrical field. All right, and they found that alpha particle can be deflected, repelled by the positive pole, but attracted by negative pole. What is the charge of alpha particle? Attracted by negative, but repelled by positive. Positive. Okay, so we realize with the mass per charge ratio, alpha particle is identified as the helium atom, just the nucleus of helium atom. So 2 protons and 2 neutrons. Now I give you some example there. So if you look at the mass number, so reduced by 4, and the atomic number reduced by 2. Okay. All right, the next one we have beta radiation. So beta radiation comes out and can be deflected by electrical field as well, but this time is go toward positive pole, but get repelled by the negative pole. What is the charge of these beta particles? If you know, that's the negative charge. This is an electron. Okay, so like here we go. So the mass per charge ratio is identical to that of electron. So we have either electron or we call beta emission, beta particle, same thing. Okay. So what actually happened is in beta radiation, the neutron spontaneously decays. So we lose 1 proton. We lose 1 neutron, but this neutron turns into 1 proton and 1 electron. That's why you get 1 electron right there. All right. So here's how this works. So look at the math right here. The iodine loses a neutron. So the mass number is supposed to be from 131 goes down to 130, right? But this neutron turned to be another proton. That's why the mass number stay the same. Lose 1 neutron, gains 1 proton, so stay the same. But the atomic mass 53 goes up to 54. All right. So we have more proton here and release an electron. Okay, or if you want to make this really correct, so we this emission come from the nucleus, so we call this electron a beta particle. So we use the beta sign here. Okay, so occur when a nucleus spontaneously decay. Usually happen with a nucleus that has too many neutrons. We can talk about later how many neutrons that a nucleus can have, but some of them have way too many neutrons, and those happen. They usually undergo a beta radiation. Okay, decay to proton and an electron, which is ejected from the nucleus. Decay results in the increased number of proton. Here we go, got a proton there, and electron is ejected from the nucleus. All right, one more. So we have gamma radiation, which is the most powerful radiation, like compared to alpha particle and the beta radiation. Okay, so this radiation has no mass or charge. So this gamma is just a power, just an energy coming out of the nucleus. And since it doesn't have a mass or charge, this gamma radiation does not affect the mass number or the atomic number. Stay the same. We use star to show that this nucleus has very high energy and ready to emit the gamma ray, basically. You're going to see quite a star quite a few times. Okay. And so since it doesn't have charge, the gamma particle just go through magnetic field or electrical field, just go pass through it. All right, one question. So you have to think a little in here, okay? So nucleus A, so we have started with nucleus A. So this is nucleus, no electron in here, okay? Decays twice to form B and C, respectively. So become B, become C, so decay twice. Identify which decay is an alpha emission and which is a beta emission. All right, start with an alpha particle. Releasing an alpha particle, what happened to the nucleus? For example, right? This is an alpha particle coming out, right? So alpha radiation. The mass number reduced by 4, right? And the atomic number reduced by 2. Okay. Basically, what happened is when alpha particle comes out, which is helium, the number of neutrons reduced by 2 and the number of protons reduced by 2. All right. From A to B, take a look. So on the x-axis, that is number of proton. On the y-axis is number of neutron. A to B looks like number of protons lower by 2 and the number of neutron lower by 2 as well. That is an the alpha emission. Okay. All right, next one, identify a beta emission. So beta emission, so release an electron from the nucleus. Okay. So neutron decay become a proton and 1 electron. Now neutron become proton and an electron. So what happened is, so we lose one neutron, but we gain 1 proton. See that? So which one? So from B to C, we lose 1 proton, 56 to 55, but we gain 1 proton, 31 to 32. That is a beta emission. Okay. It takes some time to be familiar with all this number, but you get a hang of it. All right. So we got 2 more. So 5 total, 3 down, 2 more to go.